Hello class, this is Mrs. Ayodeji with today's video on 11.2 Polynomial Functions. As you're watching the video, please feel free to pause, rewind, and replay the video as often as you need so you can get a clearer understanding of what is occurring. Don't forget to write down important formulas, vocabulary, and equations. And at the end and conclusion of watching the video, write a brief summary about what occurred in the video and submit that summary as well as a deep, thought-provoking question via the online WISC the night before class. All right, let's begin. Today we're going to be talking about polynomial functions, and you've actually been working with polynomial functions since middle school, but we're going to build on what you've been working with to have a more general understanding of what it means to be a polynomial function. By definition, a polynomial function is a sum of power functions whose exponents are non-negative integers. Last video we talked about what power functions were, and they have exponents, but in this case for polynomial functions, the exponents have to be non-negative integers. If they do have negative integers or not even integers but just rational numbers as their exponents, then it is not a polynomial function because it's not made up of power functions explicitly whose exponents are non-negative integers. So let's look at an example based off real-world example that you guys always seem to ask, when will this be applied in real life? Well, here's an example. We're going to start with that. So let's say you make 5 separate deposits of $1,000 each into a savings account. One deposit per year beginning today. What annual interest rate gives a balance in the account of $6,000 5 years from today? So over 5 years, if you deposit $5,000, what interest rate will allow you to accrue exactly $1,000 over the 5 years? Well, in order to figure out that question, we're going to set up a mathematical model based off of the concept of applying interest and accumulation. So let R be the constant annual interest rate in decimal format. We don't exactly know what R is. That's what we're going to be determining after we set up this mathematical model. So on September 9th, 2016, let's say, for example, we deposit $1,000 in the bank account. And then a year from then, September 9th, 2017, we deposit another $1,000. So the question is, how much is in the bank account at the end of the first year? Well, the amount that's in the bank account is the previous initial amount that we deposited, plus the interest earned on that initial deposit, and then plus the $1,000 that was deposited at the end of year 1, beginning of year 2. This process will occur for the next year, which occurs and ends in 2018. The balance at the end of that second year is the balance from the end of the first year plus the interest earned during that second year plus the new deposit of $1,000. So we repeat this process until we get down to the 5th year. And the end of the 5th year, the balance will be determined by the sum of the balance from the end of the 4th year plus the interest earned on the sum of the balance from the 4th year. And since we've already included the 5 $1,000 deposits, we don't need another additional deposit. Well, in order to come up with an expression of this in terms of R, we're going to need to change from this recursive formula, that's a word you'll use in the future in chapter 13, to a more formula that's based entirely not on previous years, but just based off of R, the interest rate R, or some other variable including R. So let's take a look at an example. Back to the original one. If you take a look here, what we've done is we repeat this value from the end of the first year, but if you look at it, B naught plus B naught times R is the same thing as B naught times 1 plus R. So I'm going to replace 1 plus R with the expression X. So then this becomes B naught times X plus 1,000. And we know that B naught is 1,000. So the end of the first year, our expression in terms of X is 1,000X plus 1,000. We do the same thing for the end of the second year. And we end up with this expression to represent the balance at the end of the second year. We do this for the end of the third year, the same process, all the way down to the 5th year. and we end up with this. And some of you may say, why do we end up with this? Well, if you remember, the red $1,000 was the first $1,000 that we deposited, and it's actually earning interest on itself for 5 years. So that's why it's x to the 5th. The blue 1,000 is the $1,000 deposit from the beginning of the 2nd year, and as you see, it's being added over and over. And then the blue again is the end of the beginning of the 2nd year. That's being added interest 4 times, and the green is the 3rd deposit, and that's being added interest 3 times, and vice versa. And so we get this expression right here, and that's helpful because now we have an expression to determine the end of the balance after 5 years, and that expression is only in terms of one variable, and that expression looks very much like a lovely polynomial function, and this is what that represents. We do some dividing. Now we want to set that polynomial function equal to 6,000 because that's exactly what we want the balance to be at the end of 5 years. And by doing that, we divide both sides by 1,000 and get all the terms to the left, and we end up with this expression. And we want to know when this expression is equal to 0 because that will tell us what x needs to be so that we can get $6,000 at the end of 5 years. Well, when graphing this function q of x, we end up with a root or a 0 right around a little past 1, and actually 1.0614. So this means since x is around 1.0614, that means that the rate R, the interest rate that we need so that we can get a balance of $6,000 after 5 years, would have to be 0.0614. And if you don't believe it, test it out and see. And I'll wait for 5 years. Just kidding, I won't. Okay, moving on. So a general expression for the family of all polynomial functions looks something like this. And this terminology may be a little bit new, so I'm going to go over it very quickly. These constants with a's in front of them are called coefficients, and they're related to the respective power. Okay, so we say a sub n is the coefficient of x to the n. So a sub 6 is the coefficient of x to the 6, and vice versa. Each of these coefficients can be any type of number. They can even be 0, with the exception of the first coefficient with the highest power. That cannot be 0. So all the other coefficients can be 0 except this coefficient. And we call this coefficient the leading coefficient, or the leading term, because it's so important it can't be equal to 0. So this is the leading term, or the constant term, and it cannot be equal to 0. Okay? To write a polynomial in standard form, we arrange it in terms from highest power to the lowest power, going from left to right. So here are some examples of polynomial functions. This is not in standard form because the highest power is not to the left. So to rewrite this into standard form, we would have to put the 4x to the 5th as the first term, then the negative x to the 3rd, then the 3x squared, then the x, and then the 1. And this is what we have right here. Okay? Now, some of you may notice that there is no x to the 4th power term. There is, but the reason why we can't display it is that the coefficient of x to the 4th is 0, which is why it's not there. So the coefficients of this polynomial in decreasing order are 4, 0, because there's no x to the 4th term, negative 1, 3, 1, and 1. Even this term right here, even though it doesn't have an x term, if I do x to the 0, that represents the constant term. So, constant number. Now, what do these graphs look like? Well, like in the previous example, even power leading coefficients have restricted ranges, whereas the leading coefficient is odd, it doesn't have restricting ranges. But all polynomial functions have no asymptotes. All polynomial functions are not discontinuous. In other words, they are continuous, and all polynomials have all real numbers as their domain. Okay? What is the relationship to power functions? Well, this is the expression here. But what it really means is that for any polynomial function, piece of x, if the leading term, or the leading power, or the highest power is n, then that means that the polynomial looks like the power term function as well, as long as x is big enough, or x is really, really negative big enough. Okay, what does that mean in the picture? Very quickly, here we have a polynomial 10 times x to the 7th plus 150x to the 6th, vice versa. And then here we have it compared to just 10 times x to the p. And as you can see, if you zoom out for very large x, those functions are indistinguishable because at the end they seem to both be going to infinity. But if we zoom in, we can see that they're very different at the lower level. So the long-term behavior is that as x goes to infinity or negative infinity, the polynomial looks very much like the power function, and those function values go to infinity and negative infinity respectively. If you look here for an even power function, the same works, except that all the function values are going to infinity. Alright, that's it. I hope you enjoyed the video. Please feel free to do the examples, and I'll see you in class.